Okay, believe it or not, we are still talking about intermolecular forces. This time we're going to talk about solutions in intermolecular forces and how intermolecular forces can affect the ability of things to dissolve in liquids. So we've covered some of these terms and ideas in Chem 110, but just to refresh everybody's memory, a solution is usually a liquid with one or more things are dissolved in something else, and there are a couple of terms that you need to know. The things that get dissolved are called solutes. The things that do the dissolving, the liquid, usually it's a liquid. The liquid that does the dissolving is called a solvent, and everything mixed together is called the solution. So unfortunately, all those words sound the same, but you kind of need to know what they mean precisely. So, for example, if I say that we're working with salt water, the salt is the solute, the water is the solvent, and the whole mixture together is called the solution. And there are a couple of things that I want to say about solutions with respect to intermolecular forces. The thing that I want to discuss is something called solubility. Solubility is basically how easily a material dissolves in some other material. So here I've got a beaker of water. These are supposed to be sugar cubes. I can put a lot of sugar cubes into water. So what you say is that table sugar has high solubility in water. You can dissolve an awful lot of it in water. This is supposed to be gold, and if you've probably never tried to do this, but you could try to dissolve gold in water. I'm sure a very, very, very tiny bit might dissolve, but pretty much almost all of it will not dissolve. So you would say that gold has very low solubility in water. And there's everything in between, right? Some things can dissolve a lot, some things can dissolve a little, and there's things that might dissolve somewhere in the middle as well. And the amount that you can dissolve is in a liquid is called solubility. I can dissolve a few cubes of sugar in my Dunkin' Donuts coffee, but I probably can't dissolve 5 pounds of, 600 pounds of sugar in my Dunkin' Donuts coffee. And basically what I want you to realize is there's a limit, right? The way that I think about it is there are a certain number of, spaces in your liquid that can accommodate whatever you're trying to dissolve. And so, there are a certain number of spaces or places in my Dunkin' Donuts coffee that can dissolve table sugar, and there are a lot of them, but I can reach the limit, right? I can throw so much sugar into my coffee that a bunch of it dissolves, but some of it just can't be dissolved. So liquids usually have a limit for how much of something they can dissolve. And that is usually called a solubility limit. A couple more technical terms. If you have not hit the limit, if you've dissolved certain amount of stuff in your liquid, but you could dissolve a little bit more, then you say that your liquid is unsaturated with whatever you're trying to dissolve. If you have hit the limit, or if you've gone over the limit, then you say that your liquid is saturated with whatever you're trying to dissolve. So what does this have to do with intermolecular forces? Basically, the amount, the solubility limit, especially in water is what we're going to talk about, is affected by how much the water likes to, is attracted to whatever you're trying to dissolve. So the idea here is that if there's more attraction between water and whatever you're trying to dissolve, then the solubility limit will go up. If there's less attraction between water and whatever you're trying to dissolve, the solubility limit will go down. And so here's an example with some data. This is 2-propanone, which I already showed you before, also known as acetone. And acetone, there's the structure of acetone. This part here, like I said, it has a little bit of a negative, partial negative electrical charge, and that part basically likes to interact with water. This part here, tiny bit of a positive, but not quite so much. And a lot of this molecule is hydrophilic. In other words, a large portion of the molecule likes to interact with water. And if you measure how much acetone you can actually dissolve in water, you don't really hit a limit. It's just called miscible, which means you can mix as much as you want between acetone and water, and it will all mix. But then if you start to look at materials that are similar to acetone, like this one over here, this one is acetone with a little bit more, another carbon and a few more hydrogens tacked on, and this part doesn't like to mix with water. But I just made a big chunk of this molecule, a part of the molecule that doesn't like to mix with water. So water likes to sort of interact with this part, and maybe that part a little bit as well. But there's this big chunk of 2-butanone that doesn't like to mix with water. So if you measure how much 2-butanone you can dissolve in water, there's a limit. You can only dissolve 25.6 grams of 2-butanone for every 100 milliliters of water, even though it's very similar to acetone, which you can dissolve as much as you want of in there. And the reason that you can't dissolve as much as you want is because you've started to add this chunk to the molecule that doesn't like to interact with water. So again, the lesson is the more water likes to interact with a molecule, in general, the more you'll be able to dissolve of that molecule into water. And then if you look at another similar compound, this is very similar to acetone as well, but it's got an even bigger chunk that doesn't like to mix with water. And if you look, the solubility limit is even less, right? It's only 4.3 grams. It's only 4.3 grams per of 2-pentanone for every 100 milliliters of water. Compared to 2-butanone, you can dissolve more of 2-butanone in water because there's less of this stuff that doesn't like to mix with water when you compare it to this one down here. And this one is even bigger, and this one is even bigger still. And you can see that the solubility limit goes down and down and down. So again, the punchline here is that if water is attracted to large portions of your molecule, then the solubility limit of that molecule will go up in water. If there are big chunks of the molecule that don't like to interact with water, then that molecule will not dissolve as easily in water. Here is another thought exercise. These are all different alcohol molecules, and if you remember from the refresher video, these are called alcohol functional groups. And alcohol functional groups tend to have partial negative and partial positive charges. Partial negative, partial positive, partial negative, partial positive, partial negative, partial positive on the oxygen and hydrogen atoms. And the only thing different between these molecules here is these chunks here, and these chunks are relatively hydrophobic. That means they don't like to mix with water. And it says rank these alcohols from most soluble to least soluble in water. So you should pause the video and think about which ones will dissolve the most and which ones will dissolve the least. So if you unpause the video, basically this molecule here, propanol, has the smallest hydrophobic area compared to the other ones there. And so it has, this part of the molecule water will like to interact with, this part of the molecule water won't. But this is the smallest chunk compared to the others. So this one is going to be number 1 as far as the ability to dissolve in water. It will have the highest solubility in water. The one that is second is this one because that is the second biggest chunk. So that will be number 2 as far as the ability to dissolve in water. This is number 3 because it is the third smallest, and this is number 4. This one will be the least soluble or have the lowest solubility in water compared to the others. So here's a summary of everything that we've been talking about. Atoms and molecules can be attracted to each other. There are all sorts of different kinds of attractions. There are covalent bonds and ion-ion attractions or ionic bonds. These are the strongest up here. There are ion-dipole interactions. That's when you have something with a full-blown positive or full-blown negative charge, and it interacts with something with partial positive or negative charge. So that's kind of second strongest. There are dipole-dipole interactions. That's when you have things with partial negative and partial positive charges that are attracted to each other. A special type of dipole-dipole interaction is hydrogen bond, and traditionally you draw hydrogen bonds with a dotted line. And then the weakest attraction is London dispersion forces, which are basically attractions because of temporary dipoles or temporary partial electrical charges or imbalances on atoms and molecules. And basically you can measure attractions by measuring boiling point or viscosity, or whether things like to dissolve in other materials. So basically, the larger the number of attractions, the higher the boiling point will be. The larger the number of attractions, the higher the viscosity will be. The larger the number of attractions, the greater ability you will have to dissolve in some other material. So that is it for intermolecular forces.
When you were here before, couldn't look you in the eye. You're just like an angel. Your skin makes me cry. You float like a feather, and I'm beautiful.